I'm Randy Appel, and I'm your Regents tutor. And in this lesson, you're going to learn everything you need to know on the Regents about bonding. Bonding happens to be one of those topics that I, as a teacher, find students have a very difficult time with this. So I'm going to try to make it very easy for you. Now, Regents tutor's philosophy is everything should be made easy to you. But this one is especially important, so make sure you pay attention especially close to this one. The basis for all bonding, and understanding this is half the game. The basis for all bonding is that every element wants a full valence shell. So on the periodic table, you know every single element on the periodic table wants a filled valence shell. So they want to either gain electrons or they want to lose electrons. And that will get them a filled valence shell because they want to be like noble gases. The reason why noble gases don't bond is because noble gases don't have to bond. Noble gases are already happy. So you bond because you want to gain or lose electrons, and you'll see exactly what that means. You have to know properties of forming bonds and breaking bonds. When you form a bond, and you got to think of all these atoms. Remember, all atoms want to bond. Think of all these kids with a lot of energy, or all these people with a lot of energy. They're dating, they're going on dates all the time, meeting different people. And then all of a sudden, they form a bond with someone. Just like atoms form a bond with someone. What happens to all that energy they had? Well, a lot of it, unfortunately, gets lost. Because now they're stable. They're happy. They don't have all that energy anymore. They don't have to do all those things they used to do. That's the same thing with forming a bond. When you form a bond, you get more stable and you release energy. A light should have just gone off in your head and you should have been like, oh, he released energy. He must mean it's exothermic. And you're exactly right. Forming a bond is exothermic. It gets more stable, you release energy. And the more energy that you release, the more stable the bond was. That's when you're breaking a bond. When you're forming a bond, the more energy that's released, the stronger the bond is. When you're dealing with breaking bonds, how do you break a bond? Well, you have a bond. How do you break it? Just like keeping it like this is not breaking a bond. You have to add energy. It absorbs enough energy and eventually it breaks. So breaking a bond is actually endothermic. And now it's like when two people are dating and they break up, they now have all this energy that they used to have. So when you break bonds, you release energy. When you break bonds, you absorb energy. Okay? And the more energy that is absorbed, the stronger that bond was. So in order to break a bond, you have to add energy. Now, you can't understand bonding unless you understand Lewis structures and how to draw a Lewis electron dot structure for atoms. For atoms, what Lewis dot diagrams represent, they have dots around them. And the dots represent valence electrons. So writing a Lewis dot structure for an atom is a joke. It is so easy as long as you know what a valence electron is. Let's talk about, let's say we want to draw bromine. Or actually, let's do B, which is boron. If you want to draw the Lewis structure for boron, the first thing you do is you write the symbol for boron. Then you figure out how many valence electrons are there. Now you look at your periodic table on the screen, and you see the electron configuration is 2, 3. So that means that boron has 3 valence electrons. You just have to write 3 dots. Does it matter where you write the dots? Not 100%. But I'm going to teach you the right way to do it. The right way to do it is you can only have 2 electrons on either side. Remember, what's the maximum amount of valence electrons you can have? 8. So 2, 2, 2, and 2 is 8. But boron doesn't have 8. It has 3. So the first thing you do is whichever side you start with, and it doesn't really matter which side you start with, but the first side you start with, you draw 2 valence electrons, if you can. So boron has 3. That's 2. And then you start going around one at a time. But boron has 3, so it looks like that. Let's say we want to do oxygen, which has some more valence electrons. Oxygen has an electron configuration of 2, 6, which means it has 6 valence electrons. So, does it matter if I start on the right? No, let's start on top this time. It doesn't matter. I start with 2 and I want to get 6. Now, I go 1, 2, 3, 4, and now I'm done because 4 plus 2 is 6. So I went 2 up top, then 3, 4, 5, 6. Now you may be thinking, how is the Regents going to know whether I started here? The bottom line is, for the Regents, you just need the right number of valence electrons. I'm just teaching you the proper method and the order in which you write them. And then, just to be safe, let's just do neon. Neon has 8. Start over here. 1, 2, 3, 4, 5, 6, 7, 8. And that's showing the Lewis dot structure for atoms. All right. Using the Lewis dot structure will help you understand bonding much more. What you need to understand now is the two major types of bonding that we deal with. And that is ionic bonding and covalent bonding. The first one I'm going to talk about is ionic bonding. There are many things you're going to learn about ionic bonding. But the major thing you need to know is that it's a transfer of electrons between a metal and a nonmetal. It's a transfer of electrons between a metal and a nonmetal. Transfer, good, okay, you know it's transferring electrons, and it's a metal and a nonmetal. Let me show you what happens with ionic bonding. Let's say you have potassium chloride, which you know from formula writing, and you could check back to the concept on formula writing for how to write formulas. But potassium chloride is KCl. The way you draw the bonding of KCl, well, you know it's a metal and a nonmetal. And you know that, again, you could check on the concept from the periodic table, the lesson on the periodic table where we talk about metals and nonmetals. Potassium, let's draw the Lewis structure first. Potassium has 1 valence electron. So its dot structure looks like that. Chlorine has 7. Now, what does potassium want to do? Potassium has 1. It wants to get a full shell, so it has to lose 1 electron. So it wants to lose. Wants to lose 1 electron. And the E negative just represents an electron because it's negative, because it's really important that you remember that it's negative. What does chlorine want to do? Well, chlorine has 7 electrons, and it wants a full shell. So it wants to gain 1 electron. So chlorine wants to gain 1 electron. Don't they make a perfect pair? Potassium wants to lose 1. Chlorine wants to gain 1. So there's going to be a transfer. Ionic bonding is transferring. Metal and nonmetal, because metals want to lose, nonmetals want to gain. When they want to do different things, there's going to be a transfer. So this electron gets transferred over here. Now you're not done. I just showed you what happens in an ionic bond. You have to then show me what happens, because sometimes they can ask for the Lewis structure of ions. Now remember, if this transferred an electron, it then becomes an ion. When it loses an electron, this is the new Lewis structure. How many valence electrons does it have? 0, because it lost it. So it's potassium. But you also have to write the charge. If it loses 1 electron, it's a +1 charge. And we don't have to always write +1. We could just write plus, and that implies +1, because it lost electrons. Chlorine gained 1 electron. So does chlorine also have 0 valence electrons? No, it has 8, because it gained 1. 1, 2, 3, 4, 5, 6, 7, 8. Chlorine now has a charge as well. And when you have valence electrons, you have to draw brackets around them to show. Now I'm just going to erase this because it looks like it's part of it, even though it's not. And this was just from up here. But this chlorine now has 8 valence electrons for a total charge of -1. And that is an ionic bond. And now in an ionic bond, you have, ions. An ionic bond forms ions. And the positive, you may be thinking, well, just because, so this one transferred an electron, why does it have to bond? Well, now you have positive charge and a negative charge next to each other. That's called an electrostatic force when a positive and negative bond together. And that's what happens. The positive and the negative bond together, and now you have potassium chloride. And this is how you designate it. Notice there's a transfer of electrons. One of the things you have to understand with ionic bonds is anything that's bonded ionically is called a salt. So this ionically bonded substance, KCl, is an example of a salt. Most people think of salt as NaCl, sodium chloride, but anything that's ionically bonded, where there's a transfer of electrons, represents a salt. Now, what's the relevance of electronegativity? Well, sometimes they ask for ionic and most ionic or least ionic. You may have learned in your class that in order to tell if something's ionic, the electronegativity difference between the two atoms has to be greater than 1.7. And that's true. But what I want you to do, and the Regents tutor method of figuring out whether it's ionic or not, is you take a metal and a nonmetal, and that's ionic. But sometimes they say, which of the following is the most ionic? And then you need electronegativity. Now, you can refer back to the concept on electronegativity, but I'm going to tell you what it is again. Remember, electronegativity is how much an atom wants to gain an electron. So, how do we figure that out? We go to table S. Potassium has an electronegativity of 0.8. Potassium is 0.8. Chlorine has an electronegativity of 3.2. The electronegativity difference between the two is 2.4. It's greater than 1.7. So it's ionic. Now remember, the greater the difference in electronegativity, the more ionic they are. Because why would something have a high electronegativity difference? Because one guy wants to do one thing, gain electrons, and the other wants to lose electrons, so it has a low electronegativity. So the greater the difference in electronegativity, the more ionic the substance is. And that is understanding one part of bonding. And that's only one part, because there's a lot more to bonding than just ionic bonding. To sum up ionic bonding, you need to know there's a transfer of electrons between a metal and a nonmetal. You produce ions, both one positive and one negative, or more than one positive and one negative, but you produce positive and negative ions. They're called salts. Anything ionic is called a salt. And the electronegativity difference is greater than 1.7. And the greater the difference, the more ionic. The next thing we need to talk about is covalent bonding. Covalent bonding, well, unfortunately, it's a little more difficult, but it doesn't always have to be. The reason why it's more difficult is because there's two types of covalent bonding. There's polar covalent bonding, and there's nonpolar covalent bonding. Let's first talk about polar. I'm going to give you an example of a covalent bond first. HCl is a polar covalent bond. Well, first thing, covalent bonds, before I even go any further, covalent bonds are between two nonmetals. So ionic was a metal and a nonmetal. A covalent bond is between two nonmetals. And a covalent substance is called a molecule. A covalently bonded substance is called a molecule. That's what a molecule is. Now let's talk about polar bonding. You have HCl. Well, any kind of bonding, you need to draw the electron dot symbol, the Lewis structure. Hydrogen has one valence electron, and chlorine has 7. What does hydrogen want to do? Now you may think, oh, hydrogen wants to lose an electron. But remember, hydrogen on the periodic table is all the way to the left. If it loses an electron, it has no electrons. It wants to have a filled electron shell like helium. So hydrogen really wants to gain one electron. Chlorine also, as I said before, wants to gain one electron. Now they both want to gain. So what's going to happen? Instead of transferring an electron, they're actually going to share an electron. So it's very important that you understand that covalent bonding is the sharing of electrons. How do you remember that? Covalent, C, S, sharing. Caring is sharing? Well, covalent is sharing. Covalent bond is when you share electrons. So what's going to happen is, what I'm going to do right now is I'm going to, instead of put the dot, I wanted to leave the dot there at the beginning, but I'm actually going to change it to an X. Why would I change it to an X? Well, I want to differentiate between the Lewis dot structure for hydrogen and the Lewis dot structure for chlorine, because the bond is going to look like this when they share. That's a polar covalent bond. That's it. Well, let's talk about why it's covalent first. It's covalent because it's two nonmetals. They're sharing electrons, okay, between two nonmetals. Now, another way to write this is with a bond. When you see bonds, that's what you're referring to. Now, here, this represents the electron donated by hydrogen, and this represents the electron donated by chlorine, because they both donated one electron. This is where polarity comes in. We have to think about electronegativity. Yeah, they're both sharing electrons, but is one of them pulling a little harder? Let's see what the electronegativity, because that represents how much it wants to gain an electron, or the attraction for electrons. Hydrogen has an electron configuration, has an electronegativity of 2.1. Chlorine has an electronegativity, as we talked about before, of 3.2. They're both sharing the electrons. The electrons are both here. They're sharing them. But one of them is pulling a little bit harder for those electrons. And which one's pulling harder? Well, chlorine has a higher electronegativity. So chlorine is pulling a little bit harder than hydrogen. So the electrons are closer to chlorine. Therefore, we call that, they're not ions, and I designate this symbol. This means slightly. This is slightly negative, and this is slightly positive. And I brought a friend of mine here to demonstrate this. My chem geek friend Steven's going to come in. Thank you, Steven. Now, as a chemistry teacher, you tend to be friends with other chemistry geek teachers. Steven is a chemistry geek. Now, I'm obviously much stronger than Steve. So when we're sharing this ruler, let's say right now we're sharing it. But since I'm stronger, I'm going to pull, and the electrons are going to be closer to me. Now, we're both sharing it. We both have the ruler, but a ruler is closer to me. So now I have more of the ruler than Steve. So it's an unequal sharing. Thank you. Just like with HCl, there's an unequal sharing. Chlorine is pulling a little bit harder. So chlorine is slightly negative. Now, there's a negative pole or a negative end and a positive pole or a positive end. Wait a minute. Positive end, positive pole, negative pole. Oh, this must be polar. And it is. This is a polar molecule because there's a positive pole and a negative pole. This is the negative pole, this is the positive pole, because there's an unequal sharing. So anytime you have two elements that have different electronegativities, you have an unequal sharing. Let's say I wanted to draw H2. That's two hydrogen atoms together. Hydrogen and hydrogen. They both want to gain one electron, so this is what their bonding looks like. Now, the electronegativity of hydrogen is 2.1. And the electronegativity of this hydrogen is also 2.1. Which one's pulling harder? Neither. They have the same pull. So they're sharing these electrons equally. Therefore, this represents, there's no poles, no one's pulling any harder than the other. This is a non-polar bond. Non-polar bond because they have the same element. Polar bond because they are different elements. But we're not completely done with polar and non-polar. It's actually gets a little bit more complicated, or maybe a little bit more easy, depending on how you look at it. To really understand the difference between polar and non-polar, you have to understand this. Yeah, SNAP. SNAP. S-N-A-P. if the molecule is symmetrical, it's nonpolar. If the molecule is asymmetrical, it's polar. Well, let's look at here. Symmetrical means if you cut it down the middle, any place in the middle, cut it down the middle, top to bottom, left to right, diagonally, and you folded it over, it's exactly the same on both sides. Well, a hydrogen and a chlorine are very different atoms. So if you cut it down the middle and folded it over, it's not symmetrical. It's asymmetrical. So it's polar. Two hydrogen atoms bonded together. If you cut it down the middle, no matter where you cut it, it's exactly the same atom. So it's going to fold over perfectly. That is symmetrical. So if it's symmetrical, it's nonpolar. Sometimes, though, you can have a special type of nonpolar molecule. CH4 looks like this. And in fact, carbon, with anything that has 4, when it has 4 attached to it, so CH4, CCl4, CF4, CBr4, those are all, they look just like this. Now, each bond here is polar, right? Because carbon's pulling differently than hydrogen. Carbon's different than hydrogen. Carbon's different than hydrogen. Carbon's different than hydrogen. So there are 4 polar bonds. But the molecule as a whole, cut it down the middle, fold it over, cut it down the middle, fold it over, is symmetrical. So this represents a nonpolar molecule, because it's a symmetrical molecule, with polar bonds. So a lot of the times on the Regents they say, why is this substance why is this substance polar? Or what makes a substance polar or nonpolar? And all you need to know is if it's symmetrical, it's polar. So if they said to you, why is this substance polar? You say it's asymmetrical. Why is this substance nonpolar? You say it's symmetrical. And more or less polar, the more polar it is, okay, the more polar it is, that means the more different it is. So that if they ask for which is the most polar, you take the electronegativity values, and whichever has the greatest difference in electronegativity represents the most polar bond. Least polar has the least difference. Okay, that is polar and nonpolar covalent bonds. Now just to sum up covalent bonds are between two nonmetals. There's a sharing of electrons. The electronegativity, of course, is greater than 1.7, and it could be polar or nonpolar. If it's symmetrical, it's nonpolar. If it's asymmetrical, it's polar. Next thing we have to talk about are Lewis structures for compounds. Now we just drew them, but I have to specifically talk about Lewis structures for compounds. So let's say we want to do ionic compounds. If I want to draw the Lewis structure for calcium oxide, the first thing I have to do is, again, I have to draw the Lewis structure. But to draw the Lewis structure, what I need to do is let's figure out how to write the formula. Calcium oxide, remember, Ca is +2, oxygen is -2. You can refer back to this with writing formulas section, the concept on writing formulas. Crisscross, you have Ca2O2. You have to simplify it, and it's CaO. How would I write the Lewis structure, though? Well, calcium has 2 electrons, and oxygen, valence electrons. Oxygen has 6. And what does calcium do? It transfers 2 electrons. 1 here, and 1 here. So the Lewis structure of calcium oxide looks like this. Ca with a 2+ charge, and an oxygen that's filled 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, so make it brighter. 3, 4, 5, 6, 7, 8 with a 2- charge. Now notice I wrote brackets here. I don't have to write brackets for the one that has no electrons, but it's just, if it's easier for you to do it that way, then do it that way. But the whole point is, for Lewis structures for ionic compounds, you need to show brackets, at least for one of them, the valence electron difference, and the charge. And that's the same way you do it for an ion. If they said the calcium ion, this is what the calcium ion looks like. If they said the oxide ion, this is what the oxide ion looks like. And you also have to know how to draw the Lewis structures for covalently bonded substances, which are a little different. Actually, a lot different. So let's talk about how. Let's say you have NH3, because I'm just going to use examples, because the Regents uses the same examples over and over. If you have NH3, you have nitrogen, which has 5 valence electrons. So I draw 1, 2, 3, 4, 5. And since it's NH3, where do you think the 3 H's are going to go? Well, each H has 1 valence electron. It's going to go right here. And again, the X just represents so you can see which one's hydrogens and which one's nitrogens. That represents NH3. That's ammonia. Another way to draw that, simply just going N, 2 dots, H bond here, H bond here, H bond here. And that's NH3. Another one that's commonly asked is H2O. So I'll go over H2O. H2O, oxygen has 6. 1, 2, 3, 4, 5. 6, sorry. And there's H here, and that's H2O. Again, you could draw it like this. And that's H2O. That's water. Now notice, water is a polar molecule because it's asymmetrical. That will come into play a little later on. There are a couple of more covalent substances that you need to know about, and I'm just going to show them to you because they're a little hard to figure out how to draw, but the Regents just want you to memorize them. And it's carbon dioxide. Carbon dioxide has a Lewis structure that looks like this. Do you have to know how to draw other substances with double bonds? Not necessarily. And nothing like this. Carbon dioxide is the only one you need to memorize. So it looks like this. And notice that carbon dioxide is another example of a nonpolar molecule, because it's symmetrical, with polar bonds. And then sometimes they may ask you about diatomic molecules. Hydrogen wants to gain 1 electron, and another hydrogen wants to gain an electron, so they share 1 electron. Oxygen needs 2 electrons. O2, oxygen has a double bond because they each need 2 electrons. And remember, these are just the Brinkelhoffs. And the only weird one, aside from oxygen, is nitrogen. Nitrogen has 5 valence electrons, so it needs 3. So if it bonds with itself, it shares 3 electrons. And another thing you need to notice before we go on is that each bond represents 1 shared pair of electrons. In other words, 1 bond represents 2 actual electrons. And those are the Lewis structures. And sometimes people have trouble with this stuff, but if you understand exactly what we just went over, there's nothing you need to know, nothing more than that. There's another kind of bonding that we need to talk about, and that's metallic bonding. Metallic bonding is the bonding within a metal. This is a piece of metal. This spoon is a metal. This is a piece of copper metal. These are all metals. Now, with metals, the reason why metals conduct electricity is because in metallic bonding, the electrons are moving around the whole entire substance. So the valence electrons move from atom to atom to atom to atom. And because these electrons are mobile or moving, we call it, for metallic bonding, there is a sea, like a sea, an ocean, but a sea of mobile electrons. And the mobile electrons are what makes metals conduct electricity, because negative charges or positive charges are what makes substances conduct electricity. And when you're dealing with metallic bonding, it's just a bonding between a metal. It's not two different metals. It's the same metal bonded together. Like in this copper, this is just many, many, many copper atoms bonded together metallically in a copper metal. It's a copper solid that's metal metallic bonding. Last thing you need to know about this kind of bonding is the properties of ionic, covalent, and metallic bonding. First, you have to know the melting point. Ionic substances, since they're strong, have a high melting point. Same with metallic bonding, high melting point. Covalent, low melting point because they're a little hard. They're easier to break because the bonds are a little weaker because they're just sharing. That's that. Hard or soft? Ionic, hard. Metallic, hard, except for mercury, which is a liquid. Covalent bonds and substances are soft. So that's another property. And the last property you have to know about is conductivity. Ionic substances, or salts, are not conductors of electricity in the solid phase. Because even though there are positive and negative ions in an ionic substance, they're together. In order for something to conduct electricity, they need to be free-flowing ions. So an ionically bonded substance, as a solid, has all the ions together. The only way that an ionically bonded substance can conduct electricity is if you drop it in water or turn it into a liquid. And then the ions can move around. And then a solution or an aqueous solution of an ionic substance is conductive. So as a solid, it's not conductive, but as a liquid or aqueous or a solution, ionic substances are conductors of electricity. Metallic, of course they are conductors because remember they have those mobile electrons. And covalent, they're molecules. There are no ions in a covalently bonded substance, so there are no conductivity there. Not at all. And the last thing we have to go over is intermolecular forces. Molecular, you should think of, molecules. Intermolecular forces are forces between two different molecules. And we're generally talking about two different polar molecules for the regions. So let's say we have water. Remember, this is the Lewis structure for water. Let's say we have another water. Because when you have a cup of water, or a flask of water, or a beaker of water, what's happening here? You don't have one water molecule, right? You have many, many water molecules bonded together. Well, in each water molecule, there are polar covalent bonds. But here, you have many water molecules attracting each other that keeps them together. And what happens is, if you think about polarity, oxygen has a higher electronegativity than hydrogen. So oxygen, remember, this is slightly negative, and the hydrogen part is slightly positive. So all the hydrogen parts are slightly positive, and the oxygen parts are slightly negative. What happens when two polar molecules come in contact with each other? The negative pole of one attracts the positive pole of another. So there's actually some attraction between these water molecules. And that's what happens in a substance of water. There's attraction between the water molecules. When you boil water, you're actually breaking those bonds and turning it into a gas, and then there are less attractions. These are intermolecular forces because they're forces between molecules. They're weak forces. But there is a strong type of intermolecular force. And a strong type of intermolecular force is called hydrogen bonding. And that's when the hydrogen of one molecule bonds to the oxygen, fluorine, or nitrogen of another molecule. Oxygen, fluorine, or nitrogen. So here is hydrogen bonding. This is a relatively strong type of intermolecular force. And again, it's between hydrogen and oxygen. So in H2O, it shows this hydrogen bonding. If you have H2O as a liquid, if you have HF as a liquid, also H and N, NH3 as a liquid, or any phase. There is a stronger type of attraction because these three substances show hydrogen bonding. So whenever they say, why are the forces stronger with these, or what accounts for the relatively high boiling point of water, like why does it take a lot of heat to boil water? It's because water has hydrogen bonding, and so does NH3, and so does HF. Well, you learned a lot about bonding in this lesson. We went over a lot of things, and it was probably a little consuming, but you have to understand all of it. And now that you heard the lesson, I really want you to go over the questions. Make sure you know every question, every answer, and listen to every video explanation, even if you think you know it already. And if you still have a problem, I want you to come chat with me or chat with your Regents tutor. What you need to do is you need to know that you always have a Regents tutor there to chat with you when you need it. Also, use the questions. But between all of that, you'll be fine. So I hope you enjoyed. Hope you learned something.